Hey class, this is just a short overview. We're going to talk about the continuity equation, which is an expression of the equation, the conservation of mass for a fluid system. A lot of this should be a review from your prior fluid mechanics class, and we're going to be applying it primarily in an algebraic manner in this class. First, just to start off, we'll talk about the idea of a control volume. And control volume is just some sort of three-dimensional volume that looks like this. We're going to be considering this fixed relative to us, the observer, so we're not going to consider moving control volumes. And generally speaking, fluid will be flowing through this control volume like this. We'll have a coordinate system down here, x, y, z. And some of the key things, one is the control volume will have a normal vector. This vector points normal to the surface and outward. That's just by convention that points normal outward, but has an effect on the minus signs when it comes to flux calculations. This is a normal vector. It's of length 1. And I will consider a differential element of the surface of this control volume. So this is a very tiny little element of the surface that has area ds. Now the total amount of mass that's in that control volume at any time is given by the triple integral, the integral over the volume, rho dv. Where dv is the volume differential. It's a tiny chunk of the volume in here, and rho is the density of the fluid in that tiny chunk. So rho is a function of x, y, z, and t, and if we integrate over the volume at a given time t, the density, we get the total amount of mass that's in there, and if we're using MKS, we get kilograms. So that's the total mass. Then we have how much is coming in or out of the control volume. So at any time we can have velocity flowing through there. If velocity is flowing normal to the edge, then it will be carrying fluid in or out of the control volume, and that will lead to changes in mass in the control volume. So we have to look, what's the flux of mass through the surface at any time? That's an integral over the surface of the control volume time what is being fluxed. That's this mass per unit volume, or specific mass, which is given by density, or rho. And the amount of the flux is the velocity dotted with the normal, ds. So if this is positive, it's positive out, just due to the nature of the normal convention being positive out. So this right here is a measure of the volume flux. V dot n is how much flow you're getting through the surface of the control volume. We integrate that over the entire surface of the control volume, and this is the flux of mass. This is in kilograms per second. Now, what conservation of mass says is mass is neither created nor destroyed. And so we write this equation that the time rate of change of the mass in the control volume is equal to the net flow of the mass into the control volume. And I should note that I posted some lecture notes, so if you follow those, if you're looking at those as well as listening to the video, that may be helpful because I have some additional graphics in those notes. So this time rate of change of the mass is given by partial t, because the density is a function of x, y, z, and t, so we need a partial derivative. The integral over the volume of rho dv plus the integral over the surface of rho v dot n ds. So this is the time rate of change of the mass, and this is the flux out of the surface. So we can put that on the other side of the equation if we want to, make it equals minus this term. But this accounts for exchanges of mass through the surface. This is changes of mass within the volume, and those two things have to be equal. And that's a traditional expression of the integral form of the continuity equation for any fluid in 3 dimensions, or n dimensions. We can also write this, we may have seen this more commonly in differential form, which we usually write like this: partial rho, partial t, plus grad dot rho u, or u is the velocity vector again, equals 0. So this is what we call differential form. This is true at any point. Here's a tiny little point in space, and this is an expression of that same continuity equation at any point in space. And what we can do is take this grad operator, essentially it's a derivative in 3 space, and we use a product rule to undo what's here in this parenthesis. So this is equal to d rho dt plus rho grad dot u plus u dot grad, rho. So this is just this derivative essentially split into the 2 pieces here. And this thing right here is the total derivative. So we can write this as, we can write this as d rho dt, this part and this is d rho dt, the material total derivative is equal to partial rho partial t plus u dot del rho. So we can write this continuity equation as d rho dt plus rho times grad dot u equals 0. Now, what do we mean by incompressible? In the book, and Anderson makes a note of this, he says he's defining incompressible as constant density. Constant density, or rho equals a constant. But he also has a little note in his book that this is a little bit stricter than the real definition, or I guess I actually might say looser than the real definition. This what he's saying is rho is constant everywhere in the flow field of interest. If that is true, then d rho dt up here is 0. This is 0. Change in rho is 0, which therefore, and rho is not 0, that means grad dot u is 0. Grad dot u equals 0. We call this divergence-free. We say the velocity field is divergence-free. This is by definition of an incompressible flow. If it's a 3-dimensional flow, this says that partial u partial x plus partial v partial y plus partial w partial z is equal to 0. That's just that operator written out. That's true for an incompressible flow. Strictly speaking, incompressible does not mean that the density has to be the same everywhere in the flow field. It just means that along a streamline, the density is not changing. Therefore, by definition, d rho dt equals 0 is the true expression of incompressibility. You can essentially have a flow field where this parcel is one density, this parcel is another density. They're flowing along, doing their thing, going faster, going slower, but the individual density of these parcels are not changing. Even though the whole flow field isn't of the same density, it can still be an incompressible flow field if these parcels aren't changing density. So this is strictly speaking true incompressibility, although in the book they use rho equals constant everywhere. Either way, ultimately you have this expression that del dot u is equal to 0. And again, this is a divergence-free velocity field because this is a divergence of the velocity field. We also say that the velocity field is what's called solenoidal. That's an expression of incompressibility. It's quite useful. It greatly simplifies a lot of the relations that we'll look at. Of course, no flow field is truly incompressible. It's just a mathematical limit that we're going to use. In this class, and it basically divides the differences in flow, affects greatly the differences in flow phenomena. For the most part in this class, we're going to be talking about incompressible flows, and we'll connect it in next week, I believe, to the Mach number. We'll see the compressibility and the Mach number are directly related, and a rough back of the envelope cutoff is if Mach number is less than 0.3, we can consider the flow to be incompressible. There's no hard, fast rule about that. That's more That's more a good starting place. And again, the Mach number has to do with a characteristic velocity scale for the problem, maybe the speed of the airplane or speed through an engine, divided by the local speed of sound. U over C is the Mach number. If that number is less than 0.3, meaning the characteristic convective velocity speed is small, about 30% of the speed of sound, we can consider the velocity or the flow field to be incompressible, and it changes the tools set we have to make calculations. So we'll see later, typical transonic jets or the jets that we travel around in to go from point A to point B. This will not be true. So you're talking about recreational aircraft, things moving about 200 miles an hour in order for this to be true. Now we can boil down this continuity if you think about in 1D or through a variable area stream tube. So our stream tube might look something like this. And flow is moving through there, and the area is changing as it goes, such that in the beginning here we have an initial area A1, initial velocity AV1, and an initial density ρ1. And at the exit we have an A2, it might be bigger than A1 as it is here, a V2, and a ρ2. And we want to see how are these related. Well, if we are conserving mass and we have a steady problem, we have, sorry about that pop-up, we have the case again. So if it's a steady problem, we come back to our equation, partial t, the integral over our control volume, rho dv, plus the integral over our surface area of rho dot our flux, u dot n, dA, equals 0. If it's steady, this term is 0. Partial t is 0. We have no time rate of change of the flow. If we are looking as an observer at any particular point in the flow, for example right here, we will see that the value never changes. The velocity never changes. If we move to a new position, it may change, but that's a positional change, not a temporal change. So this term is gone. So basically, the flux over the stream tube is 0. Come back to the stream tube. Since this is a stream tube, there is, by definition, no flow through the walls of this thing. That's what makes it a stream tube. And if we consider, for example, a 2D airfoil and the flows coming in and going around this thing, and then we'll have a little problem associated with this in class. The flow is confined to these artificial barriers. They're not physical barriers, but these are definitions of these streamlines. So these are stream tubes. In 2D, I don't know if I would call them tubes, but essentially they're tubes. And so the flow is confined through there. So there's no flow by definition across these thin black lines. So we only care about fluxes. If we're summing fluxes, they have to be across sections of these tubes, just like they are. And we have a tube here across the entrance and the exit of this particular tube. It's steady flow, and that means the flow going in must be equal to the flow going out. If it is unsteady, we could be storing additional mass in there or not storing mass in there, but it is steady. No mass is stored, therefore the flow goes in equals the flow going out. Therefore, for our little stream tube, we have V1, A1, ρ1 equals V2, A2, ρ2. So these must balance. Now, for the special case of an incompressible flow, we have ρ1 equals ρ2. So we can cross these out. So ρ1 equals ρ2 for our looser definition of incompressibility, because rho is not changing anywhere in the problem. And this tells us that V1A1 equals V2A2, or that the velocity at the exit divided by the velocity at the inlet is inversely related to the area at the inlet divided by, or is related to the area at the inlet divided by the area at the exit, or is inversely related to the area at the exit over the area at the inlet. The key to this is that if we have a simple shape like this, and we have flow going in, again, it has to be steady flow, and flow coming out this side, and if it's incompressible, we have if this area is greater than this area, the exit is greater than the inlet, then the velocity at the exit must be slower than the velocity at the inlet. It's a fundamental thing. This area velocity relation for incompressible flow is as simple as this. And so this tells us if we have a funky looking stream tube, and it does something like this. This is a strangely drawn stream tube, but it constricts at times. So it's some kind of snake or something. We have air coming in, air coming out. We can see here as the velocity goes through that it'll be going faster, slower, faster again, slower again, faster again, slower again. So our velocity distribution might look something like this. Slow, fast, slow, fast, slow. So here's our velocity with time. Here's some kind of mean velocity with time. And it's purely related, if it's a steady and compressible flow, to the area, cross-sectional area of the stream tube. So that's an important point. Again, it's very important that you remember that this is for a incompressible steady flow, that we have this inverse velocity relation. Later we will contrast this with supersonic flow, where we see you get the exact opposite effect. So this is true for incompressible flow, constant density flow, and it's an algebraic point. All right, that concludes what I wanted to say about continuity, and I'll give a little lecture on momentum, focusing on the Bernoulli equation as well, and I'll upload both of these to YouTube where you can get them.